Uranus should not look the way we drew it. Here's the problem no one tells you. Almost the entire picture we hold of this planet's magnetic field and its inner heat comes from one spacecraft, a single 5.5-hour flyby, 40 years ago. One working afternoon to describe a world 4 times the size of Earth. Stability 0.4, style 0.7. And in 2024, someone reopened that 40-year-old data and found something that should stop you cold. The one spacecraft that ever visited caught Uranus on a freak day. A state so rare the scientists who found it estimate the planet spends less than 5% of its time in it. The dial was pinned at the far extreme on the single afternoon we were there to read it. Stability 0.35, style 0.7. So before we ask why Uranus is strange, we have to ask a harder question. How much of that strangeness is the planet, and how much is one bad photograph? By the end, you'll know which of this world's famous impossibilities are carved into the planet itself. Which ones were an accident of timing on that single afternoon? And why, knowing all this, we have not gone back to take a second look in 40 years. The reputation rests on 3 things. Uranus rolls around the sun on its side. Its atmosphere is the coldest of any planet, and its magnetic field points almost sideways, shoved off to one flank. 3 things that should not be true at once, and the whole game is working out how many of them we can believe. Stability 0.7, style 0.3, speed 1.1. Start with the clue you can almost see for yourself, because it is the one part of this story no spacecraft had to tell us. For most of human history, nobody knew Uranus was there. 5 planets were all anyone had, points of light tracked since before writing. Then, on the night of March 13, 1781, a musician turned astronomer named William Herschel pointed a homemade telescope at the sky over his garden in Bath, England, and caught a small disk that belonged on no chart. He thought he'd found a comet. He was wrong. He'd found a planet, the first one discovered through a telescope. In one night, Herschel doubled the size of the known solar system. Stability 0.4, style 0.6. And here is why the tilt matters more than any reading from 1986. You do not need a probe to measure it. Point a good telescope at Uranus. Watch its moons and rings trace circles around it, and the angle is written plainly in the sky. 97.77 degrees. The axis lies almost flat against the orbit. This planet does not spin upright like a top. It rolls around the sun on its side like a bowling ball knocked off its feet, which does something no other planet does. As it crawls along its 84-year orbit, one pole aims almost straight at the sun for years on end, baking in continuous daylight, while the other faces out into the dark. The year splits into 4 long seasons, each about 21 years wide. A single pole can sit in unbroken sunlight for decades, then unbroken night for decades. One winter on Uranus outlasts most human careers. And the planet lies there through it, on its side, taking it. A tilt like that demands an explanation. Planets are born spinning upright. They form from a flat turning disk of gas and dust, and the spin comes out roughly aligned. To lay a whole world flat on its face, something has to knock it there. Hold that thought. This is the one clue we can trust without reservation, and it will not stay alone for long. Stability 0.7, style 0.3, speed 1.1. The second clue we can trust is the temperature, and it is stranger than the tilt. Here is the setup. The farther you get from the sun, the less heat you receive, so the outer planets should cool down in order. Neptune is the last big one, almost 1 billion miles beyond Uranus. By that logic, Neptune should be the coldest planet in the solar system. It isn't. Uranus is. Stability 0.4, style 0.7. The top of the atmosphere on Uranus drops to 49 Kelvin, minus 224 Celsius, minus 371 Fahrenheit. It holds the record for the coldest atmosphere of any planet in the solar system, and it took that title from a planet living much farther from the fire. Picture the far corner of a room turning out colder than the spot pressed against the radiator. That is Uranus against Neptune. One piece of honesty, because it matters. Coldest atmosphere among the 8 planets. Not the coldest object anywhere. Out past Uranus, Neptune's moon Triton sits near 38 Kelvin, and Pluto runs colder than Uranus too. Small worlds can go lower. But among the planets, nothing beats it, and nothing about where it sits explains how it won that title. And this reading, like the tilt, does not hang on one bad afternoon. Voyager measured 49 Kelvin. Ground telescopes and later observations have kept the cold in the same place. The coldness is the planet, not the snapshot. Stability 0.4, style 0.6, and the cold is only the skin of it. Go down far enough and the core is thought to run near 5,000 degrees Celsius, 9,000 Fahrenheit. A furnace at the middle, a record-breaking chill at the top. Keep that pairing in mind because it comes back to bite us. So we have 2 things we can believe, both carved into the planet and not into any single reading. A world lying on its side, a world colder than it has any right to be. That is the solid ground under this whole video. Now let's take the harder step and ask what could have laid a world like this down. Stability 0.4, style 0.6. Go back to the beginning. 4.5 billion years ago. The solar system is a shooting gallery. The planets are still forming, still sweeping up leftover rock and ice, and the space between them is full of half-built worlds looking for something to hit. A planet born in that chaos spins upright, because the disk it forms from spins upright. So how do you tip a whole world onto its side? You do not do it gently. You hit it, and not with a pebble. To move something the size of Uranus, you need a mountain the size of a small planet, moving fast, arriving at the wrong angle, a collision that would have glowed hot enough to be seen across the young solar system, then gone quiet over thousands of years as the wreckage settled. Nobody was around to watch. We are standing in the crater 4.5 billion years later, reading the crash from the dents. Stability 0.7, style 3.5. In 2018, a team led by Jacob Kegereis at Durham University ran that collision on a supercomputer again and again to see what it would take. Their answer? A body at least twice the mass of Earth, slamming into the young Uranus and knocking it over. I want to be careful with the words here because this is where a lot of channels cheat you. A giant impact is the leading theory. It is not a proven fact. Nobody watched it happen. We are reading the aftermath billions of years later. But the models keep landing in the same place. A quiet, ordinary birth does not give you a planet on its side, and a big enough hit does. It may not have been one hit. Uranus carries a family of moons circling neatly around its tilted equator, all moving the same direction. A single giant impact should have left them a mess, some going backward. So Alessandro Morbidelli and others have argued it may have taken 2 collisions, spread out in time, to tip the planet and still leave its moons in that clean, orderly line. In those same models, the debris from the smash settles into a disk and pulls together into moons, which may be part of why the satellites of Uranus circle its tilted equator instead of lying flat with the rest of the solar system. One impact or 2, the underneath is the same. Uranus was not born on its side. Something out here laid it down. That much, the tilt and a catastrophe behind it, belongs to the planet, and it survives the checks we can make from home. Now hold the tilt for a moment because the temperature has a twist of its own. Stability 0.7, style 0.3, speed 1.1. For 40 years, the textbooks had a clean answer for the cold, and it made Uranus sound dead. The story went like this. The other giant planets glow with their own leftover heat. Jupiter, Saturn, Neptune, each pumps out more energy than it receives from the sun, warmth left over from birth. Neptune throws out more than twice what it takes in. Uranus, the book said, was the exception. It gives back only as much as the sun hands it. No inner glow. A cold ball that had died inside. That was the settled answer. It was in the diagrams. It was on the tests. Stability 0.4, style 0.7. In May 2025, it fell apart. A team led by Patrick U.R. Wynne at Oxford went back and did the accounting properly. Each wavelength of sunlight coming in, each scrap of heat going out. Their result, Uranus radiates about 15% more energy than it receives from the sun. The internal heat was there the whole time, faint and hidden well enough that 40 years of textbooks called the planet dead. A second group, publishing that same year, found much the same imbalance. Two teams, 1 year, one correction. The furnace is lit. Now sit with what that leaves us. Two facts, both solid, both true at once. The atmosphere is the coldest of any planet, measured, confirmed. And the planet leaks more heat than it soaks up from the sun, measured, confirmed. A frozen face on a world with a warm interior. I am not going to hand you a tidy mechanism that ties those two together, because the honest state of the field is that there isn't one yet. Why the top of Uranus stays the coldest planet in the solar system while heat escapes from below is an open question. Something in the way this planet carries warmth from its deep interior up to its cloud tops that we do not yet understand. Hold both facts side by side, unexplained, because that gap between what we measured and what we can account for is the crack this whole story falls through. Stability 0.4, style 0.6, because the one fact the field was surest of, that Uranus was cold and dead inside, turned out wrong. It sat in the books for 40 years, which forces the question that runs under everything else here. If the science had that wrong for 4 decades, how much of the rest is standing on the same thin ground? Stability 0.7, style 0.3, speed 1.1. Here is the fact that should bother you more than any single number so far. One spacecraft has ever visited Uranus. 1. Voyager 2, launched in 1977, spent nearly 9 years crossing the solar system, and on January 24, 1986, it swept past Uranus at a distance of about 50,000 miles. It did not stop. It could not. It was moving too fast, bound for Neptune, and the useful science window, the close approach where the instruments could read the planet up close, ran about 5.5 hours. 1 working afternoon to meet a world. Think about what that means. A single set of instruments, sweeping past once at the speed of a bullet, gathering the numbers that would fill the Uranus chapter in textbooks for the next 2 generations. And in that afternoon, Voyager 2 did extraordinary work. It found 10 new moons and 2 new rings in a single pass. It took the temperature, mapped the crooked magnetic field, clocked winds screaming across the cloud tops at up to 560 miles an hour. Most of what got printed about the inside of Uranus for the next 4 decades came from those few hours. Now I want to be precise, because this is where the honesty lives. We have learned plenty since, from the ground and lately from the James Webb Telescope, which since 2023 has photographed the rings, the seasonal polar cap, even a brand new moon in 2025, a body barely 6 miles across that pushed the tally to 29. The outside of this planet we keep watching, and the picture keeps sharpening. But the magnetic field, the internal heat, the invisible machinery inside, that portrait is still built almost entirely on one 5.5-hour pass in 1986, and in 2024 that pass stopped looking trustworthy. Stability 0.7, style 0.35, speed 1.1. The third clue is the one you cannot see at all, and it is the one that broke people's brains in 1986. Most planets with a magnetic field run it like a bar magnet. On Earth, the field lines a compass follows come out near the poles, close to the spin axis, and loop through the center of the planet. Tidy, predictable. It is why a compass works. Uranus does not do tidy. Stability 0.4, style 0.7. Its magnetic field is tilted 59 degrees from the axis it spins on, almost 60 degrees off. And the center of that field is not at the center of the planet. It is shoved out toward the surface by about a third of the planet's radius. Picture a compass needle planted not in the middle of a globe, but stabbed into the side of it, angled almost sideways, and now spin the whole thing. The magnetic pole wobbles like a wheel on a bent axle. A compass on Uranus would be close to useless. When Voyager 2 measured this in 1986, it looked like the most deranged magnetic field in the solar system. Nobody had seen anything like it. For 40 years it sat in the textbooks as one more thing that made Uranus impossible. But here the clue splits in two, and the difference is the whole point of this video. Part of what Voyager saw is the planet, fixed, structural, real. And part of it may be nothing more than the weather on the day we flew through. Telling those two apart is what a team at JPL finally did in 2024. Stability 0.35, style 0.7. Here is what they found in the old data. In 2024, a team led by Jamie Usinski at NASA's Jet Propulsion Laboratory did something nobody had bothered to do in almost 40 years. They went back to Voyager 2's raw measurements from the days around the flyby, not the planet, the space around it, and read the weather of the solar wind blowing past Uranus. And they realized Voyager had arrived at a freak moment. Stability 0.4, style 0.7. In the days before the flyby, the pressure of the solar wind hitting Uranus spiked by roughly 20 times. 20 times is not a nudge. It is the gap between a calm harbor and a storm surge slamming the sea wall. A blast from the sun came through and crushed the planet's magnetic bubble inward, squeezing it from around 28 Uranus radii down to about 17. The magnetosphere Voyager flew into was violently compressed, wrung out in a state the team estimates is present less than 5% of the time. Read that back. Voyager photographed the magnetic environment of an entire planet on roughly 1 day out of 20, or rarer, and from that one snapshot we described the planet's character for 40 years. Put it in human terms. Imagine a stranger flew over your town once, on the single stormiest afternoon of the decade. Power lines down, streets flooded, doors shut against the wind. Snapped one photo and wrote the official description of your town from it. Empty streets, dark houses, a dead place. That description would sit in the record for 40 years, wrong in a way no one could catch because no one else ever flew over. Stability 0.4, style 0.6. Usinski put it plainly. Had the spacecraft arrived a few days earlier, the solar wind would have been about 20 times weaker, and Voyager would have seen a dramatically different planet. Same Uranus, different reading. So here is the honest split on that most deranged magnetic field in the solar system. The tilt of the field and its offset are the planet, measured, and they hold up. But how crushed it looked, how empty, how violent. A large part of that was the timing. We did not catch Uranus on an ordinary day. We caught it on its worst one and mistook the worst day for the whole personality. Stability, 0.7, style 0.35, speed 1.1. And once you pull that thread, more of the picture comes loose. For decades, the 5 big moons of Uranus, Mirandu, Titaniu, Oberon, and the rest, looked geologically dead. Voyager found the space around them oddly empty of the charged particles a busy magnetosphere should hold. Quiet moons, empty field. Nothing much happening. That emptiness may be one more symptom of the same freak day. Stability, 0.4, style 0.6. When that blast of solar wind crushed the magnetosphere, it may have swept the plasma right out of the system. So the moons looked dead only because we happened to check during the storm. The same compression appears to have pumped up the planet's radiation belts, which turn out to be second in intensity only to Jupiter's in the whole solar system. A fierce, energized belt around a system we had filed away as a quiet, empty backwater. And here is the part that should sting, Titania. One of those moons spends less than 4% of its orbit outside the magnetosphere, which gives us a clean way to test it for a hidden ocean under its ice if we ever go back. There may be living, active worlds out there that we wrote off as dead rock on the strength of one badly timed glance, so line the clues up in their 2 piles. On one side, the planet, a world knocked onto its side, and an atmosphere colder than any other, carved in, trustworthy, confirmed from home. On the other side, the snapshot, a magnetic field that looked insane and moons that looked dead, much of that the weather on one afternoon. Same planet, 2 very different kinds of truth. Stability, 0.4, style 0.7. So look at what we did, and be precise about it. Some of what makes Uranus strange is real, and it is not going anywhere. The tilt is the planet. A catastrophe laid it on its side, and you can read that angle from a backyard telescope. The cold is the planet. The coldest atmosphere of any planet, measured more than once holding steady. Those 2 are the genuine article. But the wildest sounding parts of the legend, the impossible magnetic field, the graveyard of dead moons, those we built from 5.5 hours of data, gathered on a day that comes less than 5% of the time. We took the strangest afternoon this planet may have had in a century and hung it in the textbooks as the planet itself. Read the caption under that famous picture, and it does not warn you which parts are the world and which parts are the storm. For 40 years, nobody could tell the difference, because nobody went back for a second frame. Stability, 0.75, style 0.3, and the hardest part is not in the past. It is now. We have not been back since 1986. Not once in 40 years. A flagship mission, the Uranus orbiter and probe, was named the top priority by the scientists who set NASA's agenda in 2023. On paper, it is the next great voyage. It has not launched. There is no spacecraft on the way. If it left tomorrow, a child born today would be finishing school before it arrived. So here is the thing to sit with. We know now that we read Uranus wrong in places. We can point to the day, name the storm, measure how rare it was. We understand with some precision how little we understand, and we are not going back to check. Stability, 0.6, style, 0.4. Step back far enough and it is almost unbearable. Out at the edge of our own solar system, close enough that its light reaches us in under 3 hours, there is a planet lying on its side in the dark. It was knocked there by something enormous, long ago. That part is the planet, and it is true. It runs colder at the top than any world we know, with a furnace underneath we confirmed only in 2025. That part is the planet too. And then there is the rest, a magnetic field we misread for 40 years, and moons we called dead that may be hiding oceans. Much of it drawn from a single glance, taken in 5.5 hours, on a day that comes less than one time in 20. Stability, 0.75, style 0.3. We did not get Uranus wrong because we were careless. We got parts of it wrong because we looked one time, and the universe happened to be in a strange mood the afternoon we did. The confident sentences about the inside of this planet rest on that one pass. Change the day, and you change the reading. There is a whole world out there we have met only as a bad photograph, and no one alive today may live to see the good one. Uranus should not look the way we drew it. The tilt is real. The cold is real. The rest was sketched on the worst possible day. That's as far as this one goes, but the edge always moves. This is Aphelo. Subscribe, drop a like if it earned it, and your next one's on screen now. I'll meet you a little further out.